All right, so I'm going to talk very briefly about a software feature that was added to the HRT, the ChromaTOF HRT software. So this feature was born out of a project that we and a bunch of other groups participated in through the EPA. It was their non-targeted analysis trial, or NTAC trial. I won't go too much into the details of the various phases here, but basically you were required to analyze some samples without understanding or any knowledge of what was in them, and you had to report back the peaks that you'd found and then assign a confidence value to those identifications. Okay, and as part of that idea of assigning a confidence rank, we were given this ES&T viewpoint from Dr. Szymanski, and if you've attended any non-target talk in the last, I don't know, 3-4 years, this has almost certainly come up. It's very, very helpful viewpoint, and really the idea here, I think, is best summarized in the final paragraph, where really the idea of this viewpoint was to put forth an idea of how you could do this ranking, but more importantly, I think, to get people to talk about how to do it, right? So the example and often shown ranking structure that was part of Dr. Szymanski's viewpoint is this one right here. And so we started looking at this, and it became very obvious that this is going to work very well for LCMS, but being that we do GCMS, this is probably not going to be the way that we're going to go. So most of all our work is going to be based off of library matches, which all the way up here at level 2. Also, there are some terms in here like exact mass and unequivocal that don't really have a mathematical value assigned to them, so it's very hard for us to implement this. So one of the things that we talked about was maybe we should design our own ranking structure and propose that to the EPA and see if we could use that. So that's what we did, and they were agreeable to it. So basically, we set up a manual ranking system that we'd use for the project that had a handful of tests that each library match needed to pass. So any presumptive identification had to have forward similarity score of at least 700. If there was a molecular ion in the peak true spectrum, it had to be within 5 ppm of the expected M over Z based off of the formula in the library for the presumptive mass. If there wasn't a molecular ion in the EI data, then we also ran these samples in CI so we could reach into the CI data and apply the same mass accuracy threshold. All the fragment ions in the EI spectra that were at least 30% of the base peak, 30% of the abundance of the base peak, had to have a mathematically possible formula given the presumptive matches molecular formula. The idea here being that if you can't account for the pieces, then the overall formula must be wrong and your presumptive match must be wrong. If there was an RI value in the NIST library, then it had to be within 50 RI units. And then the last one, it was just that the reviewing analyst had to have high confidence that that match was as accurate as it could be. So those were our group A criteria. The group B criteria were basically A criteria, sort of an A match, but something was missing. Typically, this would be things like a molecular ion wasn't present in the EI spectrum, or we couldn't find it in the CI, or, for instance, for me, if I saw there was meta, para, ortho versions of something, I would assign it a B match because there are just too many isomers for me to be able to make a definitive match to. And then the last group was C, where these ones we sort of kept on in the back of our minds for things that there was no reasonable match for. So that probably indicates that there just wasn't a library spectra to match to. So we go through and review the data, some of the initial data that we were looking at, and every one of these dots is a chromatographic feature found by the deconvolution software. We were very permissive, so there's all kinds of stuff in here. And then a chemist would spend a considerable amount of time, go through and review, and then this would be an example of a reviewed file where the A's and B's are shown. And these would be the matches that we initially reported to the EPA. So this was good, but it takes quite a while to go through all of these peak features, even when you can do things like exclude big chunks due to column bleed. There's still just a ton of information to go through here, and we thought it would be really great if we could leverage some more, basically a filter to help make this life a little easier, make life a little easier with this, and that's where the identification grading system came up. And basically what we did here is put in a software feature that does what we were doing manually during the project. So this is in the software, and I'm gonna make a quick switch real quick to ChromaTOF. So this is in the library search area. It's a optional part of the software that you can turn on, and it will run each one of those evaluations that we used as part of that criteria, our confidence criteria. Also, the software has got some internal logic checking. So right now it's flagging because it's saying that I've got a retention index window here that's wider than the filter that I'm using above. So if I make that change, then the flag goes away and everybody's happy again. So switching back to the PowerPoint. The way this works is for each test that passes, the match is awarded 1 point. If there's no test possible, so for instance, there isn't a molecular ion in the library spectra, so we don't expect to see one in the deconvoluted spectra, so that test just doesn't get run, right? So you could get 0 points. A failing result is a 1.5 point penalty. So the idea here is that failures are more punitive than the passes are rewarding, because anything that fails any of these checks is got to raise some serious suspicion. So you get a functional range here of -6 to +4, +4 being it matched all 4 criteria. So this is what it looks like in the software itself. New column appears. It says IGS score. And this is the library hit table. So these are all the presumptive matches for a given chemical feature. It's sorted by the IGS score, obviously greatest to least by default. And then right next to it is a concerns field. So anything that didn't get a perfect score will have a concerns value in here with a little code. We don't expect you to memorize those codes. So what we did is when you click on one of those fields, a little ellipse button will pop up, and then a description will be populated that says why you got a 0 or negative score, right? So for instance, in this one, it says at least one of the peak true ions with abundance greater than 300. So this is a value that was set in the data processing method. Does not have a mathematically possible formula within 5 ppm. Again, this is the threshold set by the user. Right? Same thing for the molecular ion. The library doesn't contain a molecular ion, so we don't expect there should be a molecular ion in the spectra, so no test was run. So now when we go back and apply that to those same samples, we've got our initially peak found data and all of the peak features that are in there, and then we apply this IGS with a filter of at least 2. So it had to pass 2 of those tests and fail none of them to score a value of at least 2. And what ends up happening is you get some results that look a lot like what happens when a chemist spends hours reviewing a sample, painstakingly going through all of these things. And this takes ChromaTOF runs this in literally seconds, ones of seconds. So very quickly you have a way to go through and evaluate what appear to be your best presumptive matches. And then you can do things like, I'll often do this when I'm looking at non-target data, but then I'll also then make another pass where I just lower the filter value to say, less than 2, but greater than 0. And that lets me look at the sort of the more borderline cases. And then anything below that, I probably don't ever look at, because generally speaking, there's not a library thing to match to unless there's something very interesting I want to go dig into it later. But if all we're trying to look for is library matches, that sort of stuff, this tool is very effective at quickly screening out the chaff and letting you focus on the best information right away. Okay. So again, the IGS, it's part of the HRT platform, and the real value here is that it leverages multiple pieces of information from the NIST library, well, from any library really, which are quite large. And I think NIST's 2020 library is something north of 300,000 spectra at this point for over 300,000 unique compounds. Obviously, there's some replicates in there. But any library that you have that has, formula in particular as part of the library match information could be used, could be run through the IGS software. And really the big advantage here is the time reduction on data review. When people start in on GCGC, they usually go through a couple of phases, one of which is that they're very excited that they're going to see everything. There's going to be thousands and thousands of peaks. They're going to get all of this information. And then when they sit down to review the information, they realize, oh no, I have thousands and thousands of peaks. I'm never going to be able to get through this. And using filters and the scoring criteria like IGS really helps streamline the review process.